Okay, good afternoon, everyone. I can see there are at least some of you here. I can't really see you, so please feel free to interrupt me anytime you have any question. And also feel free to post things in chat. I will try to have a glance on it, but it might happen that I just don't, don't see it on time. So yeah, please feel free to interrupt. So what I want to start with, please feel free to interrupt me anytime you have, excuse me, the YouTube live has overtaken. Anyway, I was saying that I want to start with going over a little bit of information for the exam. And I'm sorry, I'm trying to find my window with the information I prepared. Okay, here it is. So there was a question last time of whether I will allow you, like what kind of stuff you can write on the on one page that you are allowed to write your notes on for the exam. And you can write anything you want. So you are allowed one sheet of paper, so basically 2 pages. You can use any font you like. You can, generate it with, LaTeX or whatever else you like. You can use whatever font size is readable to you. And just have in mind that when you submit your exam next week when we write it, you will also submit those notes. And the reason why I'm allowing you to write whatever you want is because I think that going through and selecting what is most important for the exam is a pretty good guidance for studying. But for the same reason, I won't give you practice exam, as I expect that you will hyper focus on, 4 problems that might occur in the exam, which is not the point of preparation for the exam or exam itself. In terms of what kind of stuff you might expect, like about four-ish problems where I will give you a concrete example, a small example, and I will ask you to work out something like, for example, I will give you a distance measure and ask you, given this example, compute the distance between the pairs of examples in this set, or given this clustering algorithm, calculate how you would get to the clusters, the outcome of this algorithm, given some streaming algorithm, find most frequent items, maybe, producing signatures using fast min hashing algorithm. So any kind of algorithm we had gone over in this course, that's a reasonable thing to expect in the exam, and you will need to know how to actually apply it on a small example. I will also probably ask you some simple questions about the properties of algorithms, such as give one example where this, let's say, clustering algorithm is better than the other, or I might give you options and ask you to select all the properties that apply for a given algorithm. So yeah, these are kinds of stuff you might expect. And I want to stop here and see if you have any questions. Okay, I don't hear anything or see any questions in the chat, although I can't really see the chat. Yeah, not sure whether the chat thing will work for me, so please interrupt. Okay, so that's all about exam, which will happen next Wednesday in person at class.
Sorry.
So, yeah, go ahead.
Are all of the stuff covered until Monday in the exam?
Everything that is covered, even including today, could be in the exam. That's correct. On Monday, next Monday, we will start a new topic that will not be in the exam. So everything up to today, including today.
Thanks.
Okay. I guess then we can move on with our streaming algorithms. And okay, so first of all, I want to go, last time we talked about Misra-Gries algorithm, and I want to go over an example just to show you how you can apply it to something more concrete. So here we have a stream of data, A, So data here is each one of these letters, A, B, C, D, E. So in total, we have 40 of them. Remember, M was the size of our stream, and we have K equals 4. Now, let's try to apply the algorithm to this example. So this is the algorithm the way we have introduced it last time. Also, yeah, I forgot to mention, seems like my hand can't write that much on iPad. So last time, remember, we had to finish earlier because my hand was hurting. So I have to switch up the way I'm going to present a little bit. So basically what I've done is prepared things that are kind of mouthful. I put them on slides, and I will kind of go in between writing things down and just showing you these slides. So it's going to be like a mix between the way I was teaching before together with these slides. Yeah, I hope it works out. Feel free to, send me feedback later if you think that worked or it didn't work for you. I'm happy to hear what your thoughts about this. But for now, we'll do it like this. Yeah, go ahead, Ghazal.
Excuse me, I still don't understand why we use K-1 rather than K.
Yeah, I think this is just because, remember last time when we were doing all these derivations, so when people had proposed this algorithm, so they had used K-1 for these derivations and to show these bounds. I think it stems from that. I don't think there is anything more, meaningful about it.
Thank you.
Yeah. So basically, whatever your K needs to be for your application, you can always, you can artificially set it to one higher, and then you will get K-1, which is the one you want. So in a way, it doesn't matter, I would say, except for the derivations we have seen last time. Okay, so, all right, so here we have K equals to 4. So as Ghazal has just mentioned, we are going to actually use K-1, which is 3. And then here we know that we need to initialize our counter array and our location array. So we are going to do that. We are going to have C to be an array of size 3. And following this blue highlight, we are going to initialize it with all zeros. We are also going to have location array. We are going to actually store what is going to be our frequent elements, and we are going to initialize it with basically nones. Okay, so that's the first thing we are going to do. Then we need to go over each one of the elements we have in our stream, which are for us those letters A, B, C, D, E. So just going back to that example, let's see what we have here. We have our A's. So there are, if you count how many there are here, it's going to be 10 of them. 10 A's, and nowhere else in the sequence we have A's. So these are all the A's we have. Then we're going to have some B's. Here, you are going to have 9 of them, and you are also going to have some here. Here we're going to have 9, and here we have 4. So the frequency of B is 9 plus 4, which is 13. Frequency of A, the real frequency in this stream is 10. Then let's see what else we have here. We have C's. There is 8 C's. So the true frequency of C is 8. We have 4 D's, I believe. So frequency of D is 4. And then we have, let me pick some color, maybe purple. We are going to have 5 E's. So the real frequency of E is 5. And remember, the whole thing we were talking about last time is that we have some stream of data, we have the real frequency, and the issue we are facing is that we simply cannot afford to store all of these elements in the stream. So in this case, these letters. So we are finding a way to approximate what these frequencies are, and then we are going to choose the top 3 in our case as the most frequent elements. And again, just to not store all of them in an whatever data structure might be appropriate. Okay, so I was saying that we now need to go over our elements of the stream. So here we have realized we have first 10 A's, right? So first, I will write here the number of steps we have. We have M equal 40, so we will need to go over 40 steps. First item is going to be A, and then now we look at what the algorithm says. It says, okay, if there is an element in the location array L such that it is equal to the current element, for us, this is A right now, then we are going to increment the counter. This is not the case. Right now, we don't have anything in L. The next step says, okay, here, if there is a location where we have 0 in our counter array, we are going to increment it and put our current element to the same location in the location array. So that is the case, right? So here, this is the case. So we are going to then put our A into the counter into L and increment the counter. So counter becomes 1 and L becomes A, none, and none. Okay, and remember we had 10 A's, so we are going to have all the way to step 10, we are going to have A. And when we loop over our algorithm with the same value of A, what becomes relevant is this part, which says, okay, if you have a location in your location array that is equal to your current element, you're just going to increment the counter. And this is going to be the case all the way to the step A because nothing has changed. So we're going to have 10 on the first location in the counter, and our location array is going to stay the same. Now, things are changing. Instead of A's, we have 9 B's. So we are here at the step 11. We have now B. And again, where the part of algorithm that becomes relevant is the one that's highlighted in pink, which says, okay, if there is a location in your counter array that equals to 0, then you are going to increment that location and going to put the current element into the location array. So that is the case. We have second place in our counter array is 0. We are going to increment it to 1, and we are going to put our letter B to the second location of the location array. Okay, and this is going to be the case all the way to the step 19. We are going to have our element B, and then as with A, the place of the algorithm that is relevant is the one that's highlighted in green. So we are going to have C equals to, excuse me, here was a mistake. We didn't have 1, but we had 10 A's, so 10, 1, 0. And now we have 10, and we have seen 9 B's, so we are going to have 10, 9, 0. And our location array is not going to change, so it stays the same. Okay, after all of the B's, we had 8 C's. Again, we are going to have the same situation. We have now a position in our counter array where we have a 0, so we are going to put it to 1. So we have 10, 9, 1, and we'll have our location array equals to A, B, C. And as before, C's are going to be seen multiple times. So all the way to the step 27, we are going to see C, And because now it is in the location array, we are just going to increment its position in the count vector. So 10, 9, 8, and the location stays the same, A, B, C. Okay, now things are getting a little bit more interesting. At step 28, we have letter D. We have 4 Ds. But now we don't have a situation where this letter D is either in the location array, which is now ABC, or we have zeros in our counter vector. So now another situation becomes relevant, and that's the last part of the algorithm that says, okay, if these two things don't happen, what you're going to do is you are going to subtract 1 from each element in the counter array. So C becomes 9, 8, 7, but the location stays the same. And we are going to do this multiple times because D occurs multiple times. So all the way to step 31, because we have 4 Ds, we are going to subtract 1. So what will happen is that the counter vector looks like 6, 5, 4, but the location stays the same. All right, now we move on. We have, again, 4 Bs, which we have seen before, right? So 32 is a B, and the part of the algorithm that's relevant is the one that's highlighted in green, where now we do have B in our location array, so we are going to increment its position in the counter array by 1. So we have C equals to 6, 6, 4, and location stays the same. And again, we are going to do this multiple times. So we have 4 Bs. So we are going to go all the way to step 35. And we are going to keep increasing the counter. And we are going to get numbers 6, 9, 4. Okay, now we move on. In our stream, we have 5 E's. And again, the part of the algorithm that's relevant here is the one that says, okay, you need to reduce 1 from all the counts because this element is neither in the location array nor you have zeros in your counter vector. And we are going to do that for E, and we are going to do it multiple times. So we'll have C equals to 5, 8, and 3, right? And the location stays the same. And again, we are going to do this multiple times. I'm sorry, I'm going to switch here. So we are going to do this all the way to 39, step 39, where we'll still have E. We are going to decrease it, and we'll have then, we will actually do this all the way to the 40, but I want to make another point. So all the way to the second to last, we are going to decrease, and we are going to have C equals to 2, 5, 0, and location will stay the same. But now at the last step, we have another E, and now we have a 0 in our counter vector. So part of the algorithm that becomes relevant is the one where here, now we are going to add our letter E to the location and increment its position. So we'll have 2, 5, 1, and the location becomes A, B, E. Okay, and that's the outcome of the Misra-Gries algorithm for this specific example. So now we can go back and see what our actual top 3 elements were, because we know the true value, not something you would know usually. So you know that A, B, and C were actually the 3 most frequent elements. Here with this algorithm, you have captured A and B, but you have one false positive, which is E, which turns out to be our frequent element, which is not truly the case. So there is some error with the algorithm for sure. Another thing last time we had talked about is that there are the bounds on the on the estimated frequency for each element. And here we have
Excuse me.
Yeah,
Sorry. Could you please elaborate the location content again?
It's just an array that you add things to. So here we have defined location and counter vectors, right? Or arrays or lists, however you call them. And you're just using them.
Is it the current location that we are on?
So you need to follow the algorithm. Algorithm says that you are going over all of the elements of your stream, and then you are doing 3 different things depending on which situation you are in with the location and counter arrays, just the way I have done here. I don't know what exactly is confusing here.
Yeah, I understood. Thanks.
Okay, thank you. Emily?
Sorry, I'm still struggling with notation a little bit. Can you explain what happens when the array is or the location array is full of letters and then it comes across a letter that it hasn't encountered before again?
Yeah, so if it's full, if we have like we had ABC, then it depends what's going on with the counter vector. If counter vector has no zeros, then you are doing this last step over here. Do you see where I just made an arrow? In that step, you are going to decrease each value in the counter by 1. And if you had a situation which is now over here, sorry, just a second, here, where you have 1 0 or more in your counter array, and you have now an element that's not in the location array, you're going to put your element into the location array and going to increment the corresponding location in the counter array by 1. Does this make sense?
Okay, I see. Yeah, thank you.
All right. So what I was saying before is that last time we had defined some kind of bounds for our estimated frequency. So we had said here, I hope you see where I'm scribbling, that the true frequency minus epsilon m is smaller or equal to the estimated frequency. So we can maybe again write this down. We had that true frequency minus epsilon, and we have defined k as 1 over epsilon, which means that epsilon is 1 over k. Just a reminder, k was the number of counters, basically +1 in Grishamese. And so we had that true frequency minus epsilon m. Epsilon is 1 over k, so 1 over k times n is smaller or equal to the estimated frequency, right? So in other words, the true frequency is less than estimated 1 plus m over k. Now here for us, m over k is 40 over 10. Excuse me, 40 over 4, which is 10. So basically what this says is that your true frequency and your estimated frequency should differ at most 10. And that is the case. So for our true frequency of the letter A, we have 10. And for the estimated frequency of A, we had 2. So difference is 8, which is smaller than 10. For true frequency of B, we had 13. Estimated one is 5, so the difference is 8, again less than 10. And for E, we had true frequency of 5. We have estimated 1. The difference is 4, which is smaller than 10. So this is kind of what these bounds we have shown were saying to us. Okay, so basically that's it about Misra-Gries. Now I would like to go over another type of algorithm for finding and estimating frequencies of the elements in the stream. Any questions about this? Emily?
I wanted to ask, how do you choose like your K?
Yeah, I mean, there is definitely one thing you need to consider. The K, like the whole reason we are doing this is because you want to have smaller data structure that is estimating your frequency. So now you are remember last time we have said that the size of the space we need for this algorithm is going to be K times log n plus log m. So given your problem, you do need to think what is like how much space you actually want to have, because the space will be defined by K. So that's one thing you have to consider. Also, since we have shown this bound that the true frequency minus epsilon, which is 1 over K, so true frequency minus m over K is smaller than the estimated frequency. That gives you, as we have just worked out, some kind of relationship between how much error you allow. So again, this might be corresponding to your problem, how much you want this m over K to be. You can tweak K such that you have desired number. So definitely relevant what K is, but the exact number is going to depend on your own application.
Okay. And so you have to go over everything in A. I guess I'm thinking of it in terms of characters, like there's only so many characters that exist and the number isn't that big, but could your A be things that aren't just like simple characters where there is a larger set? Or like where would this be used?
Of course. I mean, were you here the last lecture?
I wasn't.
Yeah, so I recommend going over the recording of the last lecture, because we did talk about concrete examples. This is, of course, A, B, C, D, B, E is just a, like a random little toy example to show how you would work out the algorithm. One thing that you, I think, got wrong is that, yeah, sure, there are a finite number of letters in the alphabet, but you can produce infinite stream of data just using those finite number of letters, right? Like here we have repeated A 10 times. So you can produce very, very long sequence here, and you would need a lot of memory to actually store it. But yeah, just to kind of put you in the right mindset for the rest of the lecture, some of the applications you can think of are any kind of problem where you have lots of data coming in and you need to respond quickly. So you can't deal with large data structure where you would need even a minute to give a response. So some textbook examples are, you are maybe Google, you have your search engine, you have hundreds of millions users that are active every day. They are writing their questions to giving their queries to your search engine, and you need in the backbone under kind of capture which kind of queries are have seen it before or are frequent. And you need to do that very quickly because your user needs to respond very fast. No one will wait even a minute. So these kinds of applications are relevant, credit card transactions and so on. Any basically applications where you have lots of data coming in and people wanting the response very fast. Gazelle, I think you had a question or hand raised.
Here, given three numbers of counters, we started from the first of the literals to count. Do we always count from the first? Do we always choose literals from the first ones?
Yeah, that's a great question. As far as I know, we do, but it's a reasonable question to ask. So maybe there are variations where for some reason you ditch the first, I don't know how many, or start from a random location. I'm not aware of that. We would need to research that a little bit more. I'm just aware of the algorithm where you start from the beginning.
Thank you.
Jordan?
Okay, so I guess I did have a question about, like, I guess how this is for making things go faster? Because it seems like the algorithm is like essentially like trying to like save space rather than like trying to like save time, because you still have to like run through like everything that's inside like like all the entire stream.
Yeah, you are right. Yeah, you're correct that this is more about space. And the next algorithm we are going to talk about is going to have is going to be a little bit faster in terms of the space, in terms of the time as well, but we will still need to go over all of the elements. We are not going to have so many other loops in the algorithm itself. So for example, here, if we don't have 0 in the counter, or we don't have a place to put our new element, we are going to need to go over all of the places in the counter and decrement it by 1, which will not be the case in the next algorithm. Yeah, you are definitely right, and more correct way to explain this was that this is all about space. Dana?
I'm kind of confused why you're picking topmost frequent, like 3 elements. If K is 4, don't you have to pick 4 elements?
Yeah,
this index goes to K minus 1.
Yeah, it in a way it doesn't matter. You can then say K equals 5 and K minus 1 is 4. Again, this is related to the question that Gazelle had asked in the beginning, why K minus 1. It is related to those derivations that we have gone over last time. So in a way, it doesn't matter, you know, whatever you are looking for as a top frequent elements, you are going to adjust your K, you know, in a way to get those.
Okay.
All right, let's move on to the other algorithm we are going to talk about. So remember last time I told you there are different classes of the algorithms for finding the frequent elements. What we had talked about last time is 2 examples of counter-based algorithms. And today we are going to talk about sketch algorithms. So as we have now kind of reminded ourselves, our goal is to find a compact data structure that maintains the approximate counts of the high frequency elements in a stream. And our new idea will be that we can store a fixed number of counters and assign a counter to each item multiple times. And this means that multiple items might be assigned to the same counter. So we will have some kind of noise, right? Because the frequency of your element will be also kind of boosted by the frequency of some other elements that end up in the same counter. Okay, and now how should we go about modeling assigning each item to a counter? Well, we have a great tool in our toolbox, which is our hash functions, right? So we can use now choose some random hash function that takes elements from our domain. Remember, our domain was, we have represented it with the set from 1 to n. And you are trying to assign each one of these elements some number from, excuse me, this is not in, this is equal, some number from 1 to k, where each one of these numbers from 1 to k corresponds to a counter. And then what you're going to do is going to create an array, C of k counters, just the way we had it before. And you are going to increment the location in your counter array that corresponds to the location that your hash function is given to your current element. So let's maybe illustrate this just a little bit. So let's say we had k equals to 3. We had 1 counter, other, so we have C1. They're all going to be equal to 0 initially, C2 and C3. And we have some stream of data that we have called A. So we'll have A from A1, A2, A3, so on, all the way to AM. And now what we are going to do is we are going to take each one of our elements in a stream we are going to get the value of our hash function for that element, which is going to map our element to some number from 1 to k. And let's say that it map a 1 to value 1, which means that we are going to then put our element a1 into the first counter. Not really, we are not really storing it. We are just incrementing the value by 1. Okay, sorry, not. So C1 will be equal to 1. Okay, let's do the next thing. Next thing would be to take A2. We are going to put it in our hash function, and let's imagine that A2 had been mapped by our hash function to number 3, which means it's going to go into the third bucket, and C3 will become 1. Now, there might be some collisions, and you might take your element A3, put it through your hash function A3, and get value 1, which will end up in the same bucket as the bucket where A1 had ended up, and C2 will become 2, but not necessarily the frequency of A1 or A2 is 2. So there will definitely be some error here. And what we are going to talk about now in this lecture is how much error there is going to be. And we don't want it to be, a huge error, right? Okay, once we do this for the whole stream, what we are going to use as our estimated frequency is just going to be the value of the counter where the hash function is mapping your new query. That's going to be your estimated frequency. And as I've at least tried to illustrate to you, well, obviously there are going to be some collisions, and we don't want these collisions to be too many. So what is the error between the difference between our estimated and true frequency? Okay, that's what we are going to talk about next. I just want to stop here and see whether the general idea is clear to you.
What is the function of the random hash function? Like, does it need to be a different one, or like?
I'm not sure what do you mean by function of a hash function. Can you describe that?
Yeah, like the random hash function, can we just use like the default one, or do we need to like be generating different ones, or is there anything special going on with that?
No, you just need, for now, use only one, and you can use any one that maps elements from domain of 1 to n to 1 to k. So the usual ones you have used in the homework would be fine.
Okay.
As long as it's a random hash function. But yeah, you're getting maybe onto something, which is right now we will have only one. And we are going to talk about this difference between the estimated frequency and the true frequency when we have one hash function. But then, as you might suspect, given what we have seen so far in this course, we are going to kind of generalize this to having multiple hash functions and multiple counters, and then get a better estimate for the estimated frequency by using multiple ones. But for now, hold on, don't think about multiple hash functions. Right now, we have just one hash function and one counter. I mean, k counters that depend on this one hash function. Okay, so let's talk about this error between the estimated and the true frequency, where, again, estimated frequency is calculated by taking the value of the counter and the counter we are picking is the one where this hash function is mapping your element. Okay, so let's focus on f hat I for some choice of AI. So AI is element in our stream of data A. And then let's look what happens with any other element in our stream. So E for all other J. So there are basically two situations that might happen. One is that age AI and age AJ map to the same hash value. And if that happens, then AJ will contribute to FJ. It's going to contribute FJ, which is the frequency of the AJ, to the estimated frequency of the ith element AI. And if the hash values for AI and AJ are different, then AJ will not contribute to the estimated frequency of AI. Does this make sense? Yeah, thanks, Jordan.
Yeah, that makes sense. I have a quick question.
Yeah.
How likely is this to occur? I feel like with the hash functions I've used in like Python, I get a pretty massive integer, or I get a lot of characters. I mean, how likely is a collision using like a built-in hash function in Python?
Yeah, we are going to talk about different. We are going to touch a little bit on different kinds of probabilities. So let's maybe go over the rest of the derivations, and then if your question is not resolved, please let me know. Okay.
Sounds good. Thank you.
Okay. All right. So moving on to just bringing in the tools we need to kind of probe into what is the error between the estimated and the true frequency we get from the type of procedure we have described before with the hash function. So another thing we are going to need is to define a new random variable, which is just the indicator function we have seen many of before. That's going to be 1 if the hash value of AI equals to the hash value of AJ. So that's how we define the random variable xj. All right, so then the difference between the estimated frequency and the real frequency of the element AI is going to be only the amount we acquire by hashing other elements into the same bucket as AI, right? So all the other elements that end up in the same bucket contribute to the count of that bucket, but those are not the values of AGI. So everything that's not I, their frequency times whether they hash to the same value or not, will be the difference between the estimated and the real frequency. Make sense? I'm waiting for at least one thumb up. Okay, does this make sense why the difference between the estimated and real frequency equals to this summation? I can go over it again if not.
I was a bit fuzzy, so can you please go over it once again?
Sure, yeah. So going back to the procedure, procedures say, okay, if we will choose some random hash function h, and we are going to create an array with k values. So I remember, same as with Misra-Gries, we are going to have an array with all zeros, and there are going to be k zeros. And then the next thing we are going to do is go over our stream of data, which is just a sequence of elements A1, A2, A3, so on, all the way to AM. And for every element, we are going to use that hash function to map it to the set of from 1 to k. So we are going to assign each element in our stream some counter. And we are going to increment each one of these counters by 1 every time we had hashed an element to that value. So now let's say A1 is maps to, let me remove this. So we are taking age of A1 is going to be some element in the domain from 1 to k, and let's say it equals to 1. So every time we see A1, we are going to take the first value in our counter and increment it by 1. Every time we see A1, because although the choice of random hash function is random, the hash function itself is deterministic, as we have seen many times before. Now imagine that A3 is also hashing, has hash value 1. So every time you see A3, you are also going to increment your first element in the counter array by 1. So now think about, let's say these are the only elements in the stream that had hashed into the first to 1. So they are the only elements that contribute to the first element in your counter array. Now think about the true frequency of A1. You have seen it some amount of time, and that many times, Fi, you had increased the first value in the counter array by 1. But you have also increased the value in the counter array, the first value in the counter array by 1 every time you have seen A3. So the difference between what is estimated for the frequency of AI, which is the first value in the counter array, and what is the true frequency of A1 differs by exactly amount of time you have seen A3, right? And this is what that equation we have written in that slide is saying to us. So basically, every time you see an element that hashes to the same value in the counter array will contribute to the error for the estimated frequency of your given element. Okay, hopefully that's at least a little bit clearer. Another thing which will be for us to think about is the expectations of this error. And we want to show that an expectation of this estimate is pretty close to the real value. So if we work out what this is, we need estimation. And now we know that this difference equals to this summation. So we can write this down. Now I'm just repeating what the difference is. Then we can use the linearity of expectation to derive this further. So using the linearity, we know that the expectation of this sum equals to the sum of the expectation of Fj times Xj. However, Fj is not random. This is true frequency. So in a way, you can think about it as just a constant. So we know that this summation of this expectation equals to Fj times expectation of Xj, because Xj is the only random variable here. Okay, now we need to look into what the expectation of Xj is. So Xj is our random variable. Let me just make this color a little bit darker. So we have expectation of Xj. All right, so our Xj is just an indicator function, which tells that as soon as these two things hash to the same value, you're going to have 1 and you will have 0 otherwise. Now, using the definition of expectation, we just have two possible outcomes. One is 1, and then we need the probability of getting 1, which is the probability of these two things hashing to the same value. And the other outcome is that we have 0. So we have 0, and then 0 will happen only if these two things are differing. Okay. Now, this second term becomes irrelevant because we multiply it by 0. And what we need to work out is the probability that two elements are hashed to the same value. And that can be, in other terms, written by kind of expanding this, we know that for possibilities for our hash values are elements from 1 to k. And what we are then wondering about, what is the sum of the probabilities that HAI equals to some value L, and also AJ equals to L. So this is just expanding what this probability is. Now, because our hash values are independent of each other, then we can write this as a product. So here we have sum over L1 to K of the probability that HAI equals to L times probability that HAJ equals to L. And these hash functions are also uniform. So the probability of seeing any value from our domain, which is 1 to k, is equal. So each one of these probabilities equals 1 over k, and each one of these also is 1 over k. So what we have inside the sum is L over 1 to k of 1 over k times 1 over k. And now what is inside our sum is not dependent on the L anymore. So we just have k time, excuse me, I have written here prematurely k squared. So we have k values of 1 over k squared, which is 1 over k. Okay, and this is now our expectation of this random variable. Jordan, I think this answers your question as well of what is the probabilities of these two hash values colliding. It is 1 over k.
Sweet, thank you.
All right, so now we have seen what this expectation is, and we can write it down in our formula. So we have, I have chosen now different colors. We have a sum over j that are not I, fj times 1 over k. And now this is going to be smaller than if we just take the sum over all j's. So now we even include I. So this is going to be the case because our frequencies are non-negative. So if you just add one more frequency, of course, you are going to get a larger number. And this number here, this is when we sum all the frequencies of our element, the number we get is the number of element in our stream, which is m. So this whole thing is smaller than m over k. One thing you are going to see in textbooks, in notes, and so on, is that instead of m, you might see that see something along the lines that, okay, let's produce some vector, let's call it f, where we put all of our frequencies of our elements in the stream. So this is not necessarily m. Actually, it is. No, it's a vector of all the elements. So we have at most, let's say, n of them. So the number of unique elements in the stream. And then when we take the one norm of this vector, we get sum over j of fj, and we take the absolute value. But because our frequencies are non-negative, this is equal to sum over fj. So sometimes you will see that this expectation of this difference is smaller than the one norm of this vector of frequency over k. This is not super important. I'm just mentioning in case you see a different version of this such that you can connect it. Okay, so far we have now derived the estimation of this difference, which is going to be smaller than m over k. So depending on what m and k are, this might be fine. But we do need to choose the number of counters k such that this thing is actually small. So what we are going to talk about now is how do we tune the number of counters k for this algorithm we have seen, such that the difference between the estimated and the real frequency of each element is smaller than epsilon times. Okay. So let's work this out. For this, we will need the expectation we have just derived. We didn't derive that expectation for no reason. And one thing we are going to use here is so-called Markov inequality, which says that if your random variable is non-negative, so if, let's call it x, is non-negative random variable, then the probability that your random variable is larger than or equal than some number c, obviously c is larger than 0, is smaller or equal to the expectation of that random variable over c. And we are going to use that. So here, this probability that this the difference between these two frequencies, which is positive. Let me stop and explain why this difference between the estimated and the real frequencies is non-negative. It is non-negative because the way we have defined our algorithm is such that every time we see our AI, which is the element corresponding to frequency fi, we increment the counter. But also every time we see some other element. So it's going to be at least as large as fi because we are counting every AI, but also we are adding some noise coming from other elements that hash to the same value. It's never going to be smaller because we are not decrementing anything. We are just increasing the counter. So from the fact that we are just increasing the counter, it means that this difference will be non-negative. And because this is non-negative, then we can use the Markov inequality. Otherwise, we would not be able to do that. Okay, now applying the inequality, we know that the estimate of fi hat minus fi over now our c is epsilon times m. So the probability of the difference being larger than epsilon m is smaller than the estimate over epsilon m. And now remember that we have just shown that the estimate is smaller than mk. So we can plug this in. The estimation is smaller than m over k, and times epsilon times n give us that this probability of this happening is 1 over k times epsilon. All right, now reminder why we are doing this. We are trying to find the number of counters k such that the difference is smaller than epsilon m. So let's see what could be useful here. Let's try to define some delta to be equal to this epsilon epsilon k. So excuse me, I'm scrolling here too fast. So we have shown that this probability is smaller than 1 over epsilon times k. So this is just a nicer way that it's written in LaTeX. And we are just plugging new things here. We are defining delta to be this number here. This might remind you of those peg bounds we have talked about a while back, and that's not an accident. So now if we define delta to be 1 over epsilon times k, then we have that this probability is smaller than delta. And let's say that our delta is 0.001. That means because our k is in a relationship with delta, we know that k equals to 1 over delta times 1 over epsilon. So 1 over delta equals 1,000. And then we get that k needs to be 1,000 times 1 over epsilon, which is not really small, right? Our goal is to have the size of our counter array shouldn't be that large. This one will be at least of the size 1,000 if we allow the probability of failure to be small, which is a reasonable thing to expect. So instead of choosing delta to be 1 over epsilon times k and k being 1 over delta times epsilon, we are going to choose something else. We are going to say, okay, let our k be 2 times 2 times 1 over epsilon. So now this is not ridiculously large anymore. However, if we define k to be such, then the probability that these two things, that the estimated frequency and the true frequency are larger than epsilon times L will be smaller or equal 1 over 2, which is likely to be wrong, right? So this is not a great, this number here is too high. And now we come to something I have kind of hinted at before when I was answering question to Emily, which is that, okay, this is bad, but if we are using multiple copies of the whole thing we have defined before, such that we use multiple hash functions and have multiple of those counters, then this probability might not be so bad. And this might remind you, on the other stuff we have seen in the course where, by using multiple hash functions, we had managed to have a better estimate. So this is what we are going to do. We are going to use a number t to denote the number of independent copies of our initial data structure. And each copy will have its own independently and randomly chosen hash function. And we are going to do everything the same. And then we are just going to return the smallest of t estimates of our estimated frequencies for a given element AI. And the idea is that the smallest estimate has the least noise. Remember that we said because we are always increasing the counter, we are never decreasing it, then the smaller your estimate is, probably it's closer to the real frequency relative to the other counters. I'm trying to think whether it would be useful to maybe go back to make this point a little bit clearer. So remember, we have talked here that the difference between the estimated and true frequency is non-negative because we are always increasing the counter. So basically, the whole difference comes from counting stuff that are not AI into the counter, which corresponds to the frequency of AI. So the smaller number we have, it is going to be the closer to the real frequency of FI. Okay, I want to stop here just to kind of see whether you can connect the whole procedure we have described before, where we had one hash function with now this more hyper version where we have t random hash functions, but everything else stays the same. We are just doing the same thing t times in parallel and taking the minimum frequency at the end. Okay, I'll stop until I hear yes or no.
Maybe. So at least for like the independent copy. So we're actually like, I guess, repeating the process multiple times with like a different, I guess, array to do the counting.
Yeah, that's correct. And different hash function.
Okay.
Ananya?
I basically had the same question.
Okay, so it's clear.
Yes.
All right, great. I will present the algorithm in the standard, form of the, the same way I have shown you Misra-Gries. But we do need to figure out what are the values for t before we can actually put the whole algorithm in place. And this is what we are going to do now. So our estimated frequency for element AI in the stream A is going to, as I said, be minimum estimated frequency over all of the values j goes from 1 to t, right? Now, instead of just having one estimated frequency, we have t estimated frequency coming from repeating this procedure independently in parallel t times. And we are wondering how the probability of that estimate and the true frequency being larger than epsilon m. So let's work that out. So this is going to be the equal to the probability that basically if the mean of this t frequencies, estimated frequency is larger from fi by more than epsilon m, that means that every single one of them is larger than that number. So every estimated frequency Fij is larger than Fi by more than epsilon m. So if min is larger, then everything has to be larger. Again, these are independent things, so we can break this probability into products of probabilities. So we'll have product of j from 1 to t of probability that Fij minus Fi is larger than epsilon m. We have just shown before that when we have one of these estimates, then it's going to be smaller than 1 over 2, 1/2, right? So we know that this thing is smaller than 1 over 2. So we have that this whole thing is smaller than the product from j equals 1 to t of 1 over 2. And what we are doing here is we are multiplying 1 over 2 t times, right? Another way of writing this is 2 to the power of minus t. That's our probability. And again, this is just a nicer way to write it. One thing I missed to write here is that we did get this probability 1 over 2, but for a specific choice of k, and that k was 2 over epsilon. And again, remember, this is way smaller than 1,000 times 1 over epsilon, which was the version we were unhappy with, and the reason why we are doing this process multiple, t times. Okay, so we are going to now define, as we did before, our delta to be 2 to the power of minus t. And if delta equals to 2 to the power of minus t, then if we apply log 2, we'll get that log 2 delta, and also with minus in front. Okay, maybe I can write this down just to make it the whole derivation a little bit clearer. Okay, so here we have from here defined our delta. So delta equals to 2 minus t. If we apply logarithm 2 to this equation, we get that log 2 of delta equals to 2 minus t. So log 2 of 2 minus t is minus t, which means that minus log 2 delta equals to t. And if you remember from the operations over logarithms, that means that log 2 delta to the power of minus 1 equals to 2. And just another way of writing power of minus 2 is to take log 2 of 1 over delta equals to t. And this is basically what's written here. Okay, so if we have the number of hash functions t equal to log 2 of 1 over delta, then our probability of our estimated frequency being different from our true frequency for a given element ai is going to being larger than epsilon m is going to be smaller than delta, which is our given probability of failure. So if you remember, we had our delta before that we wished to be 0, 0, 1. And then the t was going to be log 2 of 1 over 0.001 is 1,000, right? And this is going to be approximately 10. So we are going to take 10 hash functions, but our k, the size of our counter is going to be 2 times 2 over epsilon. So our k is going to be something not super high, And we are going to have about 10 copies of such counters with the size of k. Okay, another thing I want to say before I show the whole algorithm is that now we know that our frequency, estimated frequency, is at least equal to true frequency, if not larger, because we're just incrementing things. But we also now know that it's smaller than our frequency plus epsilon m, which comes from here. And now we have worked out that since our k equals to 2 over epsilon, then epsilon equals to 2 over k. So if we plug that value for epsilon, we'll have 2 times n over k. So we get these bounds for our estimated frequency. And this inequality here, it will hold with probability 1 over delta. Sorry, not 1 over delta, 1 minus delta, because we have shown this bound in terms of probability, right? Okay, so a lot has been said here. I think it would be good to go over the algorithm with these exact values, and then I will stop and ask any questions you might have. So this algorithm I have just shown you with this t different hash function is called count min sketch algorithm. Again, as an input, we are going to get our stream of data, A1 to AM. We are also going to get some probability of failure, and we are going to get some threshold for how much we allow these things to differ, something you need to decide for your own problem. And then for the number of hash functions we are going to choose t to equal logarithm of 1 over delta, and k, the counter size, will be equal to 2 over epsilon for every single one of the counters we have, and we have t of them. We are going to choose t-independent random hash functions, h1 to ht, and then we are going to initialize a counter matrix, which will now be size of t times k, because we have t hash functions, and each one of them correspond to one counter of the size k. And we are going to randomly, not randomly, we are going to initialize it with zeros. The rest of the algorithm is very simple. For every element in our stream, we are going to get its value for each one of the hash functions hj, and we are going to increment the corresponding value in the counter matrix C by 1. And that's all there is. Okay. Questions about this algorithm? Oh, one thing I didn't mention is that once we are done, once we have counted everything from our stream of data, now given a new query, we are going to return the frequency, which equals to the minimum of the counters over the choice of hash functions, j.
I guess my question would probably be like, what is the query like saying, and like why would it be the minimum?
Yeah, so remember when we had turned our procedure with one hash function into procedure where we had multiple hash function? Then I said that the counter, which is the smallest out of all the counters for across different hash functions, that's the best estimate, because we are just counting, adding things to the counter. We are never subtracting. So basically, if you have t different counts for your value ai, so you have t different estimates fi, which we denoted with f hat I, then the one which is the smallest has basically the smallest difference from its true frequency, the least amount of noise, because everything that's different from the estimated and true one comes from other elements that had collided according to the hash function with element AI. I feel like this point doesn't come across, although I tried to say it multiple times. Let me think how else I could show this. So let's focus on one hash function, just one. So we have one hash function from domain N to domain K. And let's say we have two elements, A1 and A2. And let's say that they both have the same hash value. And let's say this hash value equals to 2, which means that in our counter, which has certain number of values, let's say K was 5. So the counter size will be 5. We are going to take the second element in the counter, and we are going to increase it by 1 by frequency of A1, the true frequency of A1, and by true frequency of A2. So every time we see A1 or A2, and we will see it FA1 times and FA2 times, we are going to increase the second value in the counter. And let's say we don't, any other element in our stream is not going to hash to this value. It's only A1 and A2. So in the end, what we are saying is the estimated frequency in case we have only one hash function is this second element. This is going to be the estimated frequency for both A1 and A2. And when you think about what is the difference between the estimated frequency for A1 and true frequency for A1, it is exactly the frequency of A2, because this is how many times we have increased this value, although we shouldn't have increased it if we were interested just in the frequency of A1. So this is the case if we have one hash function. Now, if we had multiple of them, you will have, so this is, let's say, C1, you will have C2 and so on. Then you can think about the difference between, let's say, whatever is the estimated frequency of that comes from C1 and C2. If the C1, the frequency we get from C2 is larger, that just means that we had been putting more things into the counter from hashing other elements into the same thing. And you can think everything that comes from different elements as noise. So taking the minimum is taking the frequency that has least amount of noise.
Okay, that makes sense.
Thanks. Emily?
So if you have like a count array or you have multiple of them, when you're saying take the minimum, is it like by element? So like if, say, like the first one was like 0 and then in the second one it was like 1, you take the 0? Or is it like the sum of the entire array? Or like what is the minimum?
Yeah, minimum, we read the formula, it says minimum or J, which goes from 1 to the number of hash function T. So you're looking for the specific value in each one of the counters corresponding to different hash functions. So maybe let me make a matrix. I think that will make things clearer. So we said this counter matrix is going to be T times K. T is the number of hash functions. K is the size of every counter we have. So we'll have here H1 to HD. So that's what our rows are going to correspond to. So we have here is going to be T. So we're going to have, all right, and we are going to here have K. Okay, so here we have some dots. Here we have some dots, here we have some dots. So basically, this is our array corresponding to the first hash value. I will call it CH1, CH2, all the way to, oh no, this is not good. This will be confusing. Excuse me, just a moment. So here we have C corresponding to H1, C corresponding to H2, C corresponding to H K. No, I'm not doing this right. I'm so sorry. I shouldn't have done this. So each row is corresponding to CH1, CH2, and so on to CHKT. I'll delete this one. Okay. So basically, each one of these rows here, let's say focus on one. This is the corresponding to the counter where we had only one hash function, right? And then what we are doing is we are going to, let's say, our element A1 has hashed according to H1 to the first element to number 1. And with the second hash function H2, it has gotten a value 2. So now here you will get some frequency. Let's call it frequency hat according to first hash function for the element A1. And here you are going to get the frequency according to second hash function of element A2. And better way to write this is to say H1A1, H2A2. And then imagine you just had 2 hash function, you are just going to take the min between the 2. So in short, you are repeating the process where you had 1 hash function, t times independently. From each one of them, you will get the estimated frequency for your element. And among these t estimated frequencies, you are going to choose the minimum one as the final estimated frequency.
Okay, I see. So it's like by element and not by like hash function. It can be across the hash functions.
Yeah, I guess I have hard time following like across what is across here. So for me, it's easier to think about it. You do everything t times across the independent hash functions, you get t estimated frequencies, and then you choose the minimum one. So I would say it's actually across hash functions, but maybe we are, using this across something slightly differently.
No, what you're saying makes sense. I think I'm just saying it weird.
Okay, so we are out of time. I wanted to talk more about the kind of the space analysis, also the difference between Misra-Gries and count-min, and also introduce count sketch algorithms. So next time we are going to talk more about this. For the homework, you just need Misra-Gries and count-min. So you have everything you need right now to finalize your homework. And whatever we talk next time on Monday will not be in the exam. So only everything that was covered up to today, including today, might come in the exam. Okay, have a nice rest of winter. Join us and snow. See you on Monday.